Hello to everybody, welcome to this webinar. So I'm very pleased to be able to chair this session today on nuclear decay data evaluation. As Vincent said, we have three speakers. So we will start with Xavier MOUGEOT, who will give an introduction on DDEP, and then we will have more detailed evaluation talks from Sylvain LEBLOND and Brian ZIMMERMAN. So without further ado, I won't take up any more time. I'm assuming Xavier is going to be able to present his slides directly. So Xavier MOUGEOT obtained his master's degree in the physics of particles and matter in 2005, and then obtained his PhD in 2008, studying the spectroscopy of helium-6 and 7, these exotic nuclei, using what's called the MUST-2 telescope. And this was at the spiral beam facility using the helium-8 beam. Recently, Xavier obtained what we have here in France called the HDR, which is the ability to be the director for a number of PhD students. But following his PhD back in 2008, he joined directly the LNHB, initially on a postdoctoral position, but he's been with us ever since. And he specializes in nuclear data evaluation, and more recently in the calculations of beta spectra and the associated neutrino spectra, and also undertaking experimental measurements via a setup we have here that we're developing in the lab with a number of PhD students. Most notably, though, Xavier has been involved in either the supervision or the director of 5 PhD students now to date. And as I said, he's been working at the LNHB for, well, it's almost 20 years now, Xavier, but not quite. He's published over 70 scientific articles, in particular in the reviews of modern physics or in physics review letters. And last year was awarded the Hubble Award by the journal Applied Radiation Isotopes, noting the work of exceptional value that he's been undertaking. And of course, as some of you may know, Xavier is on the scientific committee for the ICRM, and he's also the chair of the beta spectrometry working group of the ICRM. So I'm very pleased, Xavier, I'll let you take over the floor and put your presentation up.
So my presentation will not be very smart. I'm just giving you some basic information about the Decay Data Evaluation Project and the aim of this project. And I will let Sylvain and Brian show you interesting and intelligent things. So the Decay Data Evaluation Project, so right now it's coordinated by LNHB, so our lab. And it's related, of course, to the evaluation of decay data for mainly the interest of metrology. But actually, it's broader than just metrology, because it's all the data, all the decay data are widely used in different areas of science, in nuclear medicines, in reactor industries, in fundamental physics, because they also need very accurate nuclear decay data, in some studies about art. And for instance, in the Louvre Museum, there are some people with dedicated laboratories to irradiate some paintings and some divert art things, and they are able to analyze precisely these art things, and they are able to restore them very nicely. And it's also used, for instance, most of you know, I'm sure that apples are irradiated with cobalt-60 sources for many years now. So it's important to have good knowledge of the decay data for all these applications. So this is something that is very well known from, at most probably for more than a century, but from the beginning of the radioactivity studies. So there is a need for reliable and unbiased nuclear data, and with robust uncertainty estimation. And actually, this requires a rare expertise, because the evaluator needs to understand the measurements with different kind of apparatus and the theoretical predictions, and to build from this the most accurate knowledge possible on the nuclear decay data. And as nuclear physics has been studied for more than a century now, there are usually many measurements, many predictions available in the literature. So it's quite a long work to go through all the literature for just a single nucleus. And just to give you an example of the importance of this, the first international recommendation of nuclear data was done in 1931 about the radioactive constant. And it involves some very well-known scientific people, scientists. So Marie Curie, you can see also Hans Geiger, Otto Hahn, Ernest Rutherford, for instance. So all the people are well known about this, the importance of the nuclear decay data. And then, of course, beyond just the half-life of the nuclei, there are many more quantities that are required. So nowadays there are different kind of nuclear database available in the world. So you have Shenzhen from China. You have the ENDF database from the US, the Gendel library from Japan, the Jeff database for the Europe region, and you have also the atomic mass evaluations. So it's an international collaboration between China, Europe, and the US. And for nuclear decay data, basically you have two kinds of almost independent evaluations. So you have the ENSDF evaluations that comes from the Nuclear Structure Decay Data Network, which come from the International Agency of Atomic Energy, and the DDEP evaluations, so the one we are talking about today. At the origin of DDEP, so there were LNHB, but there were also other metrology laboratories. So LNHB has been involved in these evaluations for the last 50 years because it's critical for activity measurements in metrology. You need to have a certain pre-knowledge of the decay data to choose the best experimental technique to establish your primary activity measurements and to establish your standards. So we worked for a long time now on these evaluations, and we usually published our evaluation as internal reports in the table of radionuclides and in sometimes in peer-reviewed journals. So DDEP is an international initiative started in the 90s, and the focus is specific on the needs for the metrology community. So we aim at providing consistent decay schemes, nuclear data and atomic data also related to the decay, with a common evaluation methodology, comprehensive peer review process. And at the origin, it was a collaboration between LNHB and PTB and some ENSDF evaluators from the US. And new evaluators come afterwards during the time. So our evaluations are officially recommended by the BIPM through the CCRI, and they are supposed to be used by all metrology institutes for their studies. So basically, we provide recommended data to non-specialists, which means that users of this data are not supposed to have a deep knowledge of or understanding of the nuclear structure. So this is for metrology community, of course, for fundamental physics, for instance, for detector calibration, but also nuclear medicine, nuclear industry, as I said before. And the main information we provide is basically all the off-life, the Q value, so the energy available in the decay scheme by itself, all the possible ways to decay and to emit some particles and energy. And of course, the intensities and the energies and the type of transitions of emissions could be alpha, beta, electron captures, gamma emission, internal conversion. And at the end of this process, you have also all the atomic relaxation, which comes with X-rays emission and Auger electrons. And we provide symmetric uncertainties only, contrary to NSDF, because we have seen that it's quite difficult for most of our users to understand how to deal correctly with asymmetric uncertainties. So we published and we continue to publish our evaluation in different ways. So we have up to now published 8 tables of radionuclides volume. So it's BIPM monographies. And we publish also with the mini table of radionuclides. So the latest is from 2015. We would like to publish an updated version next year. And a long time ago, we also provided our software through a CD-ROM, but I don't know if there is any now computer that is able to read a CD-ROM. So we have renewed, our website a few years ago, and we have a quite fancy website, I think now, on which we provide all our evaluations and data. So the BIPM monographies can be downloaded directly there. Also, each nucleus evaluation. So the common files are provided. So it's a report detailing the evaluation procedure and the choice made by the evaluator. And also some files that are related to this data and with a specific format that can be directly read by computers and used, for instance, for a Monte Carlo simulation or anything else. And as you can see, there is an interactive periodic table on this website. So you can directly click on an element, and you can just select quite rapidly the nuclei that interested you, and you can download directly by a simple click all these files. There is also another separated web interface developed by my colleague Christophe Dulieu, which provides an easy access to the decay data, and you can quite easily find your nucleus. You can make some search, search with different criteria in terms of energies, in terms of intensities, for instance. And then the web interface with plot interactively the decay scheme, simplifying the decay scheme if you want to, if you put some thresholds, for instance, and you will have the different decay paths, and you can there are also various utilities to. For instance, recently he implemented the plot of radioactive chains, which is very nice. If you have a long decay chain for radon decay, for instance, it's very useful and very nice to see it directly. So the DDEP data are also in the European GEF database. So we are responsible at LNHB to update the decay data in the GEF database. The previous evaluation, the previous update was performed, I think it was in 2016. So it was a huge work performed by Marc, present here, and also Olivier Bercillon and Alan Nichols. And they reviewed all the possible, all the necessary decay data for the nuclei that are useful for reactors, and choose the best evaluation for each nucleus, and put all this together, including some tags results for which are very important for the nuclear reactors. So this is something we have to work on also for the next version. So just to give you an overview of the members, so we are now quite a small team, because all the members you can see here are not full-time equivalent. We are almost working on our free time, almost I would say, because at LNHB we are funded by LNE. We have the support of LNE to work on DDEP evaluations, but it's always only a part of our time that we can dedicate it to DDEP. So we coordinate the project, and we worked on evaluations, of course, but also on the review process, on the edition part, and on the publication. So my colleague Sylvain, who will present his evaluation just after, is involved in this, of course. Marc was the former coordinator and is right now a special advisor, I would say, and also a strong support, which is important. And Christophe Delieu, as I mentioned, is our technical support for all the development in the database. And we have Decay Data evaluators from all around the world. So we have Alan Nichols from the UK, Brian Zimmerman will also present you his recent work just after. We have Xiaolong Huang from China, Aurelian Luca from Romania, Rob Sherman from UK, and also Nicolae 𝐂𝐡𝐚𝐩𝐭𝐞𝐫𝐬 from Russia, even if we have some difficulties from the last 2 years to collaborate with Russia. And it's rather small. We have additional support also from people from the NSDF collaboration. But the workforce is quite limited. So we, since 2022, we try to engage some actions to renew the workforce and to have new evaluators. We reorganized some training workshops, one in 2022, another one, it was last October. And we also visited our colleague in China to try to involve them in and deepen our collaboration with them around decay data. So of course, all of this takes time to organize, and it's also it takes time, so it's taken on the availability dedicated to DDEP. So it can be difficult sometimes. This is just to give you another view of the evaluation. So since the latest BIPM Volume 8 monography, we have published 21 evaluations. Usually we put something like 30 evaluations in a volume, but we are discussing with BIPM now to see if we can not publish in BIPM monographies, but maybe in specific metrology issues. So this is still discussing. This is another, just to give you an idea of the difficulty of having a workforce which is rather small. We have evaluations performed a few years ago, but they are not reviewed nor published, of course. And so sometimes they have been evaluated several years ago. So maybe, also most probably, updates are needed before any review. As the workforce is small, and as the main interest is to perform the evaluation and not to review the evaluation. We have sometimes the problem of having reviewers. So even if you don't want to make evaluations for us, maybe you can help us in just helping us to review the evaluations. That could always already be something very important for us. So just to conclude rapidly, so this is an overview of all the DDEP evaluations we have in the database, published over the years, for the last 20 years now. In general, what we would consider as a good objective is to have no evaluation older than 10 years, because you have always new publications with new measurements, but it's very difficult with the current workforce to do this. So new evaluators would be more than welcome. If you can help us, that would be very nice. But we have also to renew the database and the related tools. So this requires times and technical expertise. And this could be a great help if someone could also help us and support us for doing all this. So thank you for your attention. And if you have questions, of course, please tell me.
Let's move on to the second talk in this seminar, which will be given by Sylvain LEBLOND. So Sylvain LEBLOND, like Xavier, is also a member of staff at the LNHB. Sylvain obtained his bachelor's degree in 2010 from the University of South Paris, and then his master's degree in 2012 from the University of Caen, which is in the northern area of France, in Normandy, which was on the new states in matter. And then 3 years later, he obtained his PhD in 2015, also from the same place, the University of Caen, and that was in the structure of neutron-rich isotopes of boron and carbon at the limit of stability. During his PhD, he undertook two study periods in Japan, one for 2 months and one for a little bit longer, 4 or 5 months, if my memory is correct. Since then, following his PhD, Sylvain undertook 3 postdoctoral research positions, one in 2016-17, which is at the University of Hong Kong, which was working on the preformation of alpha clusters in neutron-rich beryllium isotopes. Then from 2017 to 2019, he had a 2-year postdoc research, which was here at CEA-Saclay, so just in the southwest part of Paris, where he was working on, it was very much a development project, working on a camera to measure surface alpha-beta contamination. He then moved, I would say, back to a more fundamental research topic with his third postdoc position, which was at GANIL. GANIL is the French National Heavy Ion Accelerator Facility, which once again is in Caen in northern France, where he studied gamma-gamma ray correlation, angular correlations with the multi-detector, which we call AGATA. He then joined, I remember distinctly interviewing Sylvain during the COVID period, and he joined the lab in October 2020 here at LNHB as a research scientist, where he specializes in not only nuclear decay data evaluation, but also measurements, particularly the measurement of beta spectra, and he's working closely with Xavier in this field, but also looking at other decay properties, so in particular angular correlations. And Sylvain is notably the supervising the PhD of our PhD student Gail under the directorship of Xavier, who is measuring beta spectra. And to date, Sylvain has published a number of scientific articles in peer-reviewed journals.
Good morning, good afternoon, good evening, everybody. It's my great pleasure today to talk about the latest DDEP evaluation that I perform. So Xavier has given you a very nice introduction of what is the DDEP project and what we do. What I hope to accomplish with this evaluation is to give you an idea of the kind of procedure that and the way we perform the evaluation. Let's move on. and start with an overview of decay data of the cesium-137. So I think what is important is that, it's always, let's say, a story when you start an evaluation. In this specific case, as Mark said, I joined the laboratory in 2020. And in 2021, there was a joint initiative to reevaluate the 137 decay data. The idea was actually from was by Balaura Singh, that unfortunately left us dead, but that Xavier mentioned, that was our very good colleague from the NIST collaboration. And the idea was to add 3 different processes to work from the ENSDF collaboration, so the rather nuclear structure data file collaboration, from the DDEP and the CTBTO, so the Comprehensive Nuclear Test Ban Treaty Organization. And the idea was to have the 3 independent evaluation work on the decay data of cesium-137. Why is that? Because, as Xavier mentioned, we try to always renew our evaluation, and the latest work were performed in 2006 and 2017. Since the data were known to be inconsistent and there was no consensual agreement between the different evaluators, the idea was to see if with 3 independent evaluation and taking advantage of the latest publication, we could do better. So at that time, Xavier told me that it would be a good idea, as I just joined the group, that it would be a good idea that I tried to work on that. And it was actually my first independent evaluation work. So I started in late 2021, and it took me much more time than I think I and also Xavier and Mark anticipated. I finalized in 2023. Not only maybe because I was very careful about what I was doing as a new evaluator, but also because it ended up being a much more in-depth and huge work that we anticipated. Nevertheless, if I could finalize it, because I was not alone, I had all the support from the DDEP collaboration, and especially I'd like to thanks Alan Nichols, that performed the review of this work and that provided me tremendous help in the matter. So finally, this evaluation was published in 2023, first on the DDEP website online, but also on a peer-reviewed journal, namely ERI. And so today I'm going to present this result. So I think what all evaluator experience is when you're starting to learn or to work on the nuclei, what you're doing is you're going back in time. You always start at the beginning to try to understand how the nucleus was discovered. The story of cesium-137 is quite interesting, actually, and I thought it would be interesting to take a bit of time to talk about that. The cesium-137 was discovered actually in 1941, not by a very famous researcher, but actually by an undergraduate student called Margaret Malaise. She was working back then at the University of Berkeley, and she was looking for a project to perform her undergraduate studies. She went to one of the, I think he was associate professor back then, who was named Glenn Seaborg. And what he told us is that, sure, I have an idea. I have a freshly block of uranium that we have irradiated. The radio protection back then was not exactly the same. So they have the huge block of uranium freshly irradiated. And they told her, well, try to find something from there. I'm mainly interested in cesium isotopes. And she did the first chemical extraction of radioactive cesium, which was the first discovery of cesium-137. The rest of the story, so it was in 1941, the rest of the story is a bit different in the sense that Glenn Seaborg very quickly gained a lot of knowledge, especially of his work on transactinide nucleus, and he ended up getting the Nobel Prize in 1951 for his discovery of plutonium-231. On the other hand, unfortunately, Margaret Malaise could not pursue an academic career. The reason for that is that the dean of the faculty, if I'm not mistaken, was not accepting women for graduate studies. And then she had to stop. She worked for a few years, but then she ended up as an housewife. What is funny is that they did not publish the discovery of the discovery of cesium at first, and later on, Glenn Seaborg tried to come back to the work he did with Margaret, and what he did is that he sent off a letter in 1961, and the exchange they had is very funny because Margaret Malaise, who had since then almost left the field from 30 years, convey the surprise of her children learning that she worked with the famous Glenn Seaborg. And I think what is very interesting here is to note that Glenn Seaborg acknowledged very importantly his work. So I think that's a very interesting story. And I think that's the kind of story that hopefully we enjoy when we are doing Decay Data, going back in time. So if you're interested more, I could advise you to work from the work of Patton that I took most of these information there. So this information, this nuclei discovered by an undergraduate student was actually a big deal, as it's since our discovery, more than 80,000 publications were performed on this specific with this specific radionuclides. The reason for that, there's a very wide range of application. It's actually one of the main fission products, and especially the most produced medium life fission product. And therefore, it's strongly linked with the nuclear power cycle, with all the cycle, but it's used in other type of application, especially if you want to integrate, if you want to investigate structure of matter, or if you want to calibrate your detector, and so on and so forth. As such, it's in case of a nuclear cycle, it's one of the main source of penetrating gamma radiation from spent fuel after few months. And actually, it's notably famous for being one of the most significant contamination radionuclide remaining after a nuclear disaster. Most precisely, I'm thinking about the Chernobyl incident. So this young undergraduate actually discovered a very, very impactful radionuclides. And the reason for that, beyond the scope of application, is the very specific decay scheme that he has. So the decay scheme seems rather simple. The cesium-137 decay by beta minus decay. It populates the ground state and the excited state of barium-137. It's at an half-life of around 30 years and a total Q value of around 1 MeV. Most notably, the decay populates the second excited state and the ground state of the barium-137. What is important there is that the second excited state decay mainly through a very dominant 662 gamma emission, which is the only gamma emission of, well, the very dominant gamma emission of this nucleus. Therefore, the cesium-137 being very easy to produce in nuclear reactor, it becomes a very well-known and standardized, and I would say very unique calibration source for gamma detector. So, given this simple decay scheme, we could think that the decay data are well known. So if we have a quick look, as I mentioned, there were previous to my work 2 decay data evaluation, one performed by the DDEP project, performed by Decay and Valery Tchetchev in 2006, and more 1 year later, the NSDF collaboration published with Eddie Brown and Jack Tooley a second evaluation. So I've summarized quick information in the table, namely the half-life and the main branching ratio for the beta transition. What is important here is to notice that well, there are some inconsistencies, particularly in the branching ratios. So, as I said, new publications have been made since then, and the question is, can we improve the recommendation? So, during my work, I reviewed and reanalyzed all the decay scheme. In the scope of this presentation, in order to give some time to Brian to talk, I'm going to focus on the estimation of the half-life. And we are going to see, and I'm trying to explain how I obtained the half-life that we are now recommending as DDEP collaboration. So with further ado, let's move on this evaluation of the cesium-137 half-life. So the first thing when you're a beginner and you're trying to learn how to do evaluation, you are being told, well, the first thing is to learn and to gather all the information and publication on the subject. So you start. What is quite amazing is in the case of the cesium-137, there is a large bibliography available. I could identify more than 75 publications ranging from 1948 to 2006. And as you can guess, since there's a large gap in time, there's a lot of different type of experimental method. Many languages were involved, including some that I could not read. And when you're starting as a newcomer, that can be quite frightening, as you end up with 75 publications, and your first question is, how do I deal with that? Should I take everything into account? Are all the uncertainties reported in the work comparable? Are the publication independent? And hopefully, I had the help of the DDEP collaboration with the support of the collaboration, but also I did follow the DDEP guidelines. So what are these guidelines about? So I just quote the introduction that you can find online and the rule for evaluation that are advised. First of all, I discarded all private communication that could be known of a published work. Secondly, I did work on the treatment of uncertainty. More precisely, I spent a bit of time of unifying all the uncertainty. Why is that? Well, first of all, you discard all measurement without uncertainty. But then I made sure that all the uncertainty were reported at 1 sigma confidence level. That can be strange, but actually the habits and have changed over the years. And what was reported in 1950s is not the same as what is reported nowadays. As Xavier mentioned, we treat all the uncertainty to be symmetrical. So if they were reported asymmetrical, I had to find a way to derive a symmetrical uncertainty from there. And obviously, and I think that's the most important thing, as I said, the way we treat uncertainty has strongly evolved. Papers in the 50s were talking about errors. Nowadays we have strongly evolved with strong and detailed budget assessment of type A and type B. Unfortunately, you cannot compare them with former way of dealing with uncertainty. So what I end up doing is taking the quadratic sum of type A and type B if they were available. So when you have done that, it's not finished. You have to make sure that you want to take 1 publication per author or laboratory in order to avoid systematic bias. If one author has done 10 measurements, obviously you don't want to take all of them independently, otherwise you're going to give it too much weight in your final result. It also avoid problem of contamination of sources or that could report in many measurements. So what you have to do is to identify for each author and laboratory the best measurement or the most reliable one, and or to construct it. What I mean by that is that sometimes you have an author that will report several measurements, and you might consider taking one of them or making an average based on your instinct as an evaluator. Obviously, you have to be careful to identify the correlation between the measurement. I just showed an example of 2 papers published with more than 30 years difference from a Swiss group. One from Frédéric Juget, that was in 2016, and one a bit older from Gostoli. And what I end up doing is contacting Frédéric, asking him if there were any link between the 2 measurements. And actually, I did well because the data were partly the same. So if I ended up taking them independently, I would have had data correlated in my data set. So last but not least, when you're constructing your data set, you have to be careful that the results that are reported are not depending on physical constant. So in case of half-life, it's not critical, but for example, in case of some gamma intensity, it can be, for example, the conversion coefficient, and you have to be careful that these data are up to the date, and if possible to correct them, otherwise you're going to have inconsistency in between your data set. So applying all this rule, what you can do is start with the 75 publications that I had to end up with the 21, with 23 that I'm representing on the right plot. You can see the half-life reported in years with the associated uncertainty as a function of date. The half-life with this first data is varying from 26 to 33 years, with uncertainty ranging from 0.01 to 3 years. You can see that it's a very broad range. We can also see that at the beginning, the first measurement were quite inconsistent with each other, and the more we're going, the smaller get the uncertainty as the technique get refined and more consistent with each other, which means that we're going in the right direction, which is good. So you can have an instinct and as an evaluator, but what we try to do is also to rely on statistical tool to test distribution in order to get insight. So in this case, we're using what we call the chi-square test, which is basically comparing the ratio between the internal and external uncertainty. So the internal uncertainty refers as the uncertainty you can calculate in case of a weighted mean if you assume a quadratic propagation of the reported uncertainty. On the other hand, the external uncertainty is purely the statistical deviation or that you can observe from your measurement around the mean value. So basically what you're trying to see here is that if the reported uncertainty by each independent measurement are consistent with the deviation that you observe in your data set. In this case, as you can see, I obtain a large chi-square, which is actually much larger than what would expect. And what it means basically that at least one of the measurement uncertainty cannot be trusted. It can be only one, or it could be all of them. And therefore, the question there is, where do you go from there? What you can do is say, okay, if I do not trust the uncertainty, I'm going to make a non-weighted average. None of these uncertainty have a value, or at least one of them does not mean anything. So I'm going to keep a simple and do not take the uncertainty into account. If you do that, you end up with the half-life that I'm writing there, and you can see that it's very close to the previous reported uncertainty. So keep in mind, however, that these two work were performed in 2016, and you can see that we have 4 new measurements that have been performed since then, and that we are going to take advantage of. So in order to proceed further, what we need to do is to refine our dataset. To do that, we need to perform a critical analysis of each publication, which means that we have to read the paper in detail, trying to understand what is going on, and try to see if there is any experimental bias that, as an evaluator, we can identify, and if we can correct it or not. We also have to pay attention to the budget and the uncertainty assessment in order to make sure that the work was performed previously. As I said, we have seen that we had a doubt on the reported uncertainty. This is come to be very difficult, especially if you're reading all papers based on all techniques that are basically unknown to me. Obviously, sometimes you can count on work, and I base a lot my work on the reported work from Mike Wood that was performed in the 90s, where he had insight from the people that were working back then and could gather information on the oldest publication. If you apply all of this, I ended up saying, okay, there is these 6 measurements that I can trust and that I believe are the most reasonable of all. So you can see that they spawned from 1973 to 2020. The measurements are represented on the right plot as a function of publication date, and we can see clearly that there are very precise measurements which are inconsistent with each other. So the question is, what do we do with that? Is it better? Well, once again, we have to adjust what we have. So the first thing is I remove one of the measurements. So you can see that was the oldest and actually the most precise of all measurements. Why did I remove it as an evaluator? So basically, it was a mass spectroscopy measurement, spectrometry measurement, sorry. And when I had a look at the evaluated uncertainty budget assessment, I saw that they were discussing the contamination, the possible contamination of their source, but they were not taking into account they were not quantifying it. And therefore, I finally concluded that the uncertainty was strongly underestimated. As I did not know how to take it into account properly, I decided to remove completely this data from the dataset. On the other hand, there's another thing that I did on this data is to increase the uncertainty of one of the publications from Martin et al., which was an ionization chamber measurement. So 3 of the 6 measurements I'm reporting are ionization chamber: Martin et al., Schroeder et al., and Juget et al. What is strange is that Martin et al. Has a much smaller reporting density than Schroeder and Juget. What is strange also, is that there is no clear explanation. Martin has indeed a much longer period of measurement than the 2 late one, but in the 3 cases, the statistical part of the uncertainty is not dominating the uncertainty budget. Therefore, I had doubts on the uncertainty, and I tried to limit the impact of the measurement on the final dataset. To do that, what I decided to do is to increase the uncertainty of the reported measurement. So from this analysis, I ended up making my dataset of 5 measurements. Now you can see that compared to the chi-square of 11, now I have a chi-square which is much smaller. That means that my dataset become consistent. And to work on that, what I did is you can work with the unweighted mean as previously. You can see that already we have largely improved even with the unweighted. But since we have the consistent dataset, it means that we can trust the uncertainty, so we can work with a weighted mean, obtaining the value there. What I did, as I thought that I had question on the dataset, is to increase the uncertainty of the final result. So my recommendation is the following one. So it's the weighted average, 30.08 in years, with an uncertainty of 22. The reason it's increased to 22, it corresponds to the uncertainty of Martin et al. If we compare to the 2 previous evaluations, we can see that we have increased the uncertainty by almost an order of magnitude. And this is not because I am much smarter than the previous evaluator, but because I had new data to deal with. And that's why one of the key messages of this talk is always provide us data. It's very important.
I'm assuming that Dr. Zimmerman, Brian, you are here. You are connected. I think I saw you earlier.
I am here.
Well, very good. So I will do my best to introduce you, Brian. I feel like I should say this gentleman requires no introduction, but let's go for it anyway. Since I did the deed and looked up a few things on Dr. Brian Zimmerman. So Brian, well, he's an outsider because he's a chemist, but we'll accept him into this Decay Data Evaluation talk because Brian, so he studied at the New College of Florida, which sounds quite a good place to study for a bloke coming from north of England. He obtained his bachelor's in chemistry in 1987. He went on then to study at the University of Maryland at a place called College Park, where he obtained his nuclear chemistry PhD in 1992, which, although it was a nuclear chemistry PhD, it's very much nuclear structure because it was on the energy level structures of even tellurium and odd iodine and antimony nuclei. He studied four of these particular nuclei. He then went on, did a postdoc at the University of Tennessee in Knoxville, a very nice place where there was the Nuclear Data Conference back in 1994. He then started working immediately after this postdoc at NIST, at the National Institute of Standards and Technology in the US, which is based not far from Washington, D.C. So Brian held various positions starting from 95 to 2003 in research chemist. He then had 3 years where he zipped across to Vienna, Austria, and worked as a medical radiation physicist at the International Atomic Energy Agency. So he was in the Division of Human Health and Dosimetry. He did 3 or 4 years in Vienna and then returned again as a research chemist in the physics lab at NIST, where he then slowly moved up, becoming the acting leader of the radioactivity group. And since 2019, so 5 years now, he has been the leader of the radioactivity group in the physics laboratory. Of course, we all know Brian from his time as the editor-in-chief of Applied Radiation and Isotopes. He was editor-in-chief for 16 years. Congratulations, you deserve a medal for that, Brian, from 2004 to 2020. And he remains today the consulting editor. And of course, Brian has published extensively on both nuclear decay and nuclear level structures, and many, many articles on radionuclide metrology, with over 110 published articles. And what we shouldn't forget, and then I will hand over to Brian, who's going very red in the face with all of this eulogy that I'm providing him. Of course, Brian is currently the president of the International Committee for Radionuclide Metrology, the ICRM, and an all-round good chap. Right, up to you, Brian.
Thanks again, Mark, and thanks to everybody for sticking around and listening to the webinar on nuclear data evaluations. First of all, I'd like to thank Sylvain for summarizing the evaluation rules for me, so that was one thing that I don't have to take out the time to do, and also for presenting some of the equations that we use in our evaluations. So before I get started, I just wanted to mention, what Mark said, that I was an outsider because I was a chemist, but I should also mention that Glenn Seaborg was a chemist, and a lot of the other early people that that were involved with the discovery of a lot of the radionuclides that we're interested in were all chemists. But these days, there's a lot of blurring of the lines between the work that the chemists and physicists do in nuclear science these days. So what I'm going to do is I'm going to go through what I did for the complete evaluation of holmium-166. And could start off by saying that, when I first joined DDEP, I asked Mark, who was leading the project at the time, well, what nuclide should I work on? Where's the greatest need? And the reply was, well, within DDEP, we tend to take up these evaluations based on the interest of the evaluators. And so, since most of the work that I've done while I've been at NIST has been involved with medical radionuclides, all of the evaluations that I've been involved with so far have all been radionuclides that have had medical applications, and holmium-166 is one of those as well. So holmium-166 has been of interest for several decades. It sort of fell out of favor from about 2000 until about 2010, when it gained a resurgence because of a lot of applications that were being developed for a chemically similar radionuclide, yttrium-90. But noticing that holmium-166, even though it has similar chemistry to yttrium-90, it has the benefit of having gamma rays that could be used for doing imaging, and that could be used for doing treatment planning and retrospective dosimetry estimations. So some of the applications that they're being investigated were the use of radioactive microspheres, similar to yttrium-90, for liver cancer. Also, radio labeling and using it as an intratumor injection agent. Also labeling with antibodies. And has also been used with microspheres for doing radiation synovectomy for severe arthritis patients as well. It is produced in a reactor. There's two primary production routes. The first is with the irradiation of holmium-165. So holmium only has one stable isotope, and that's 165. You put it in a reactor, and you get holmium-166 through neutron capture. But also as a side product, you also get the holmium-166M metastable state, which is very long-lived, 1,200 years when producing it this way. The other production route is the neutron capture onto dysprosium-164, which produces 165 dysprosium, and then you do a capture on that to produce dysprosium-166, and then that beta decays to holmium-166. And so you could think of this dysprosium-166 as being a generator for holmium-166, and it's actually being investigated as a potential in vivo generator that you can inject the dysprosium and it'd be an in vivo constant generator of holmium-166. So one of the implications of this, the most common production route right now, I think, is still the irradiation of the stable holmium. Is that you're almost always going to get some of the holmium-166M as an impurity in your sample, and there's no chemical way of separating out. So you have to use spectroscopic methods to separate out the holmium from the holmium-166 from the holmium-166M, and if you don't, it could have some serious implications, particularly in your half-life calculations. So as Sylvain mentioned, the first thing that we do is we look to the past when we start off an evaluation, and so for the holmium-166, the most recent previous evaluations, there was a DDEP evaluation that was done by Schoenfeld and Dersch in 2004. And then the most recent NSTEP evaluation was performed by Coral Baglin in 2008. Since that time, there was an extensive reassessment of half-lives that was done by Unterweger and Fitzgerald at NIST, reevaluation of the previously published half-life values. And more importantly, the stimulus for a lot of the new data that came out is the formation of the Euromet MRT dosimetry project that involved as one of the work packages the measurement of nuclear data, in particular the half-lives and the X-ray and gamma ray emission probabilities. And so 4 national metrology institutes, CMI in the Czech Republic, LNHB in France, NPL in the UK, and ENEA in Italy, all took part in this project and contributed new nuclear data for holmium-166 almost simultaneously. And so this was a set of 4 new independent measurements that could be included in the evaluation. Another important aspect of this particular set of contributions was that most of the absolute emission probability publications that are currently in the literature, at least the ones that have the highest quality and the best explanations of how the data were arrived at and how the certainties were estimated, are all performed by national metrology institutes. And this is usually done as part of standardization exercises. I know we at NIST have started measuring nuclear data as part of all of our new standardizations now. And I would encourage all of the national metrology institutes and all of the laboratories having the capability of doing primary measurements to do nuclear data measurements as part of their experiments. You usually have to take the data anyway, either for impurity measurements or for confirmatory measurements. So you're sort of getting it for free. So I would encourage more of the national metrology institutes to undertake those type of measurements. There was also in 2020 a new set of emission probabilities that was It was published by Yamazaki et al. From our colleagues at EPEN in Brazil. So looking at the level scheme, the gamma ray placements, there are 17 gamma rays in the level scheme. And the placements were based on a level scheme proposed by Artisan et al. This was one of the only studies that included gamma-gamma coincidence data that allowed for good placements of the gamma rays into the level scheme. The level scheme itself is consistent, and this is demonstrated from intensity balances from the sum of all of the transition energies and comparison with the Q value based on the latest mass evaluation. There aren't a lot of measurements of the intermediate state half-lives, and even fewer mixing ratio measurements, but the values that are available were all taken from the NSDEF adopted levels and gammas evaluation. I could mention that there's a level at 1813 KEV that was originally proposed by Artisan, and I think that was primarily through energy sums of some of the transitions. That was not included in the previous NSTEP evaluation. There's no explanation given for that. But looking at both the paper from Artisan and the comments on the previous DDEP evaluation, I made the decision to leave that level in along with those transitions. So the level at 1813 is still in the evaluation in the current level scheme. So just briefly, the evaluation methodology, we use a tool called CCRI to organize the evaluation results, but I tend to do most of my calculations in Excel. It helps me to sort of organize things, and it gives me some degree of sort of traceability in how calculations are done. We use the limitation of relative statistical weights, especially in the case of discrepant data. And the tool that we use to do these calculations is called LWeight. And this is implemented both as a standalone code and as an Excel macro that can be used. And this is provided to the DDEP evaluators by the project. Internal conversion coefficients are calculated using the BRIC code, using the frozen orbital approximation. X-ray and Auger electron emission intensities are calculated using the emission code, the 2013 version from Schoenfeld and Janssen. The most recent mass evaluation from Wang et al. Is used to calculate total Q values. The data from Schoenfeld and Janssen are also used to calculate fluorescence yields, and the X-ray and Auger electron energies are taken from databases from Schoenfeld and Rodloff from PTB. The beta shape code from Xavier is used to calculate log FT values and mean beta energies. This is a new approach that we've recently taken within DDEP. Before that, most log FT calculations were done using the log FT program, which also helped us to calculate mean beta energies. And throughout, all of the uncertainties are quoted as a single uncertainty interval. The quantities that I've outlined here in blue are actually calculations that can be done within CCRI using the respective programs. And so we put in a certain amount of the data that's required for the calculations, and the CCRI calls these external programs and fills in the calculated values for many of these quantities directly into the database. So starting off with the half-life. So looking at the set of data going back to 1946 and going through 2020, which is the last set of recent data. One thing is clear, and this is true in almost all of the evaluations that I've done so far. And you look at the older papers, and there's not a lot of detail in how the data were acquired, what corrections were made, and more importantly, how the uncertainties, if they were even included, how they were calculated. So those values that did have uncertainties were originally included for consideration. But because we have so much new data that has a higher precision than the data that were acquired back in the 40s and through the late 60s, I decided that I would consider only those data that had greater than or equal to 2 decimal places, and that was sort of correlated with the amount of explanation and clarity in the uncertainty assessments. So running the L-weight macro, the values by Daniel and KELLETT were immediately rejected by the Chauvenet principle, and this is essentially flagging it as an outlier because it lies outside of 3 sigma from the average and the standard deviation. With those 2 data points removed, I was still getting a flag that this was a discrepant data set with an extremely high chi-square value. And so looking at the individual data points, it turned out that the data from 𝐂𝐚𝐻𝐭𝐞𝐫𝐬 was one of the culprits, as was the data from Ramanaya. And so I went back to the papers, very important thing to do, and noticed that the value that was reported by 𝐂𝐚𝐻𝐭𝐞𝐫𝐬 et al. Was based on a 1-hour measurement, so 1/10 of a half-life, or even basically 5% of a half-life, and that's simply not long enough, particularly when you have a possibility of having a long-lived impurity in your sample. So that data point was removed, and the data point from Ramanaya, the way that it was quoted and the description of the experimental the way that the experiments were carried out led me to believe that uncertainty was clearly underestimated, and so that one was also removed. There were a lot of revisions to the NIST half-life value between 2018 and 2020. So the value that was published in 2020 by Fitzgerald and Unterweger was taken as the final value from NIST. Sylvain mentioned only one value is generally taken from each laboratory as representative in the data set for consideration. There were multiple values in the publication from Boban. This was the report from the MRT dosimetry project. At least the results that were available at the time from CMI, LNHB, and NPL. Each one of those sets of measurements was independent from each other. They were done at different times with different sources. So they were treated all as independent values. And some of the laboratories reported multiple methods, and so these were combined in order to give a single value from each laboratory. And then the recommended half-life became the weighted mean of 6 of the remaining values from the original data set. So this just gives an example of the how the data are input into my spreadsheet and how the L-weight macro is used to calculate the weighted means and look for outliers. So one of the things you can see is that the uncertainty on the weighted mean is smaller than any of the values that any of the individual values that went into the calculation of the half-life. So for that reason, I expanded the uncertainty on the recommended half-life to match that of the value with having the minimum uncertainty in the data set, and this was the LNHB value. So the recommended half-life going back turns out to be 26.808 plus or minus 0.020 hours. The next step in the evaluation is generally the evaluation of the gamma ray emission probabilities. And in this case, I had 5 primary sources. The transition energies were all taken from the paper by Artisan as well. Artisan et al., and this was the same source as the previous DDEP evaluation. There are other reported measurements, including Thulium-166 electron capture decay, but none of them really improved on the data from Artisan, so those were not adopted. Of the available P gamma data published values, only Artisan was the one that did not have absolute measurements of the P gammas, and it was kind of odd that the normalization for their data. This was a 1992 publication. They based their normalization on a study that was done by Klein et al. By the Atomic Energy Commission in 1962. This was a beta gamma measurement and could be considered to be an absolute measurement that was done by sodium iodide counting, but the details in the Klein paper were not provided in how that measurement was done. Instead, it refers to an unpublished report. So taking a different approach, what I did was I calculated the mean of the normalization factors, not including the Artisan data, and then calculated a new normalization factor from the available data that could be used to renormalize the Artisan relative emission probability data. And so once that was available, I took the entire data set of the renormalized Artisan data and the other absolute emission probabilities and calculated the weighted mean for each of the individual gamma rays. A couple of the notes were the data for the 185.5 KeV gamma ray was discrepant. There were only 2 data values at the time, the one from Artisan and the NPL value reported in MOVAN. The more recent NPL measurement had a lower uncertainty and seemed to be more realistic. So that was actually chosen as a recommended value. Just my experience and my judgment as an evaluator, that being a better number. In particular, the counting statistics that were available to the NPL value versus the Artisan value were much better. And also the data for the 674.2 KeV gamma ray were also discrepant. And so I took the weighted average, but expanded the uncertainty to include the most precise value, and in this case, the one that had the smallest uncertainty was that of artisan. One thing that was very clear was that the data for gamma rays above 1250 keV were very poor in terms of counting statistics. So definitely more measurements are needed in that respect. So then the internal conversion coefficient calculations were done. As I said, we used BRIC and a number of other codes to obtain those values. And those in turn are used to calculate total emission from the levels, the transition probability, total transition probabilities. There is one transition that is of special note, and this was the transition of 1460 keV. Turns out that this is an E0 transition. For those not familiar with what this is a unique type of transition that takes place primarily between two zero plus states. They're typically forbidden according to selection rules, but the transition is possible through interactions between the nucleus and the atomic electron. So what happens is you wind up with a transition that is almost entirely characterized by internal conversion, or in some cases, pair production. This had to be calculated by a pretty roundabout way. The only experimental electron data that were done on an absolute value, on an absolute basis, that were available was a paper by Grigoriev in 1974, but it was for a transition that is not typically used in the normalization of the gamma ray data. So I had to calculate the ratio between that normalization transition and the one that was available from Grigoriev, come up with a ratio that was used to then calculate what the total intensity of the gamma ray at 1379 is. And it turns out that you get 0.905 per 100 decays, and that translates into 1.356 times 10 to the minus 3 electrons per 100 decays. So taking that electron intensity of 1460 and making the assumption that the K conversion coefficient is much larger than the other subshells, that was going to carry most of the intensity and most of the uncertainty. So the total conversion was taken as simply the K conversion coefficient in this case. And so again, for my spreadsheet, just showing how these total intensity calculations are done. And these are important because these go into the calculation of the beta branching. Now, these new recommended gamma ray emission probabilities that were calculated in the previous step go into the calculation of the total intensity for each transition, and then you calculate the sum of all of the transitions feeding into and de-exciting each level, and then you look at the difference, and any extra intensity that de-excites a level has to be due to additional intensity that's fed in by beta decay. And so that is taken as the beta branching intensity. And then the log T and the average beta energy were calculated with beta shape within Sezanuk, as I mentioned previously. So then the final step of all of this is to copy the data into Sezanuk from the spreadsheets, and then validating data entries, running consistency checks. And then unique to DDEP, we write a comments file, and this there's an extensive discussion of how each of the calculations was done, any particular decisions that were taken. And I keep a notebook to be able to keep track of all of this. That's particularly important because as Sylvain mentioned and Xavier before him, this isn't our full-time jobs. And so we don't normally have a lot of time to just sit down and go from start to finish on these evaluations. We tend to do these in fits and starts, and work on it for a week and then come back to it a month later and try to figure out what you've done. So it's very important to keep a separate notebook. So then once that's done and the peer review process takes place, and for this I have to thank Alan Nichols. He was the main reviewer on this and gave me a lot of pointers for dealing with some of the discrepant values. So this is what the current published evaluation looks like in DDEP. The first page for the tables, and then the first page of the comments file. So just to conclude, hopefully I gave you a feeling for what the process is for doing the evaluation, or at least the way that I approach these data evaluations. There is a need for additional gamma ray measurements at higher energies, and I think that's true for a lot of radionuclides these days. And from a personal standpoint, I think we make a lot of subjective decisions based on our experience and expertise. And so having experience in a lot of different experimental methods is very valuable in being able to evaluate the quality of results and the adequacy of the uncertainty estimation. And although it's not absolutely necessary, I think having some knowledge of nuclear structure physics is very valuable in looking at consistency and making sure that level assignments and things like that are reasonable. And unfortunately, programs around the world that are teaching this kind of thing, and the number of researchers that are going into the nuclear structure field is very small because of the declining number of nuclear science programs around the world. But I think we're hopefully going to see a resurgence in the interest in nuclear energy again, and there's going to be a need for people with this type of expertise. So hopefully that turns around, and with that, I will conclude.